Good afternoon, everyone. Today we're going to look at an example of graphing a function and a function that's undergone a few transformations. So our original parent function, as you can see, is the parabola graphed by y is equal to x squared, and you'll notice that it extends onto infinity in both directions. Down here we have that function that has undergone 4 different transformations, and we're going to try to graph that function in the same graph so we can kind of talk about the differences and their similarities. So let's start off by taking note of the different transformations that are at play here. So we have a negative all the way up front, which means we have, so we have in our x reflection, that is a reflection about the x-axis, right, vertically. Next, we can see that we have a vertical stretch out front of 4. We have a horizontal stretch, which we know is always 1 over the b value, which means 1 over 1/2, which means a horizontal stretch of 2, right? Then we have a horizontal translation of +3, and finally a vertical translation of +2. So again, just trying to build an idea of what these transformations look like on a graph. A vertical stretch of 4 means that for any given domain, the graph is going to be stretched out vertically by a factor of 4. So for any given domain, any restricted domain on the graph, our y values are going to be stretched out 4 times as much, okay? Now conversely, we have a horizontal stretch of 2. Now that means for any given range on our graph, for any restricted range on our graph that we're holding ourselves to, the distance that we're going to travel in x, in the x direction, is going to be twice as long. And so the graph is going to be extended twice as long horizontally, okay? Now, in keeping those two numbers in mind, we have 4 for the vertical stretch, 2 for the horizontal stretch, right? And typically we kind of connect vertical to the y's, right? I'm just going to make a quick note. And we typically think of the horizontal movement, let's say, as the x-axis, right? Because that's how our graph is defined. Now, I'll also make a note that we have the function y is equal to x squared. And I'll note that since we have y and x, 2 squared is 4, okay? 2 squared is 4. Y is equal to x squared, 2 squared is 4. Okay, I just want to highlight that really quickly before we move on to the next part of this example. Now, the reason I want to mention that is because if I were to want to pop this this new transform function onto the graph, we could certainly do that. But right now we have a lot of things going on. We have 4 transformations plus a reflection. We have a lot of things to consider and a lot of numbers to compute when we're looking at each point individually, okay? Sometimes we can do that, and we can do that right now. It would just take a little bit longer than is maybe necessary, okay? But it wouldn't be impossible. It would just be a tiny bit more tedious. Again, I want to make sure everybody understands we can still put this on a graph, no problem. The point of this example is that sometimes, especially when we're working with these well-defined functions that are continuous and go on to infinity in both directions, where the domain nor the range are restricted, sometimes the vertical stretch and the horizontal stretch kind of merge together. They kind of cancel each other out a little bit in some way, okay? And this is a really nice example of it doing exactly that. So the reason why that happens, we're going to see algebraically. So if I start to algebraically manipulate my equation here, I can write this as -4 times. Notice that the square is attached to 2 terms inside this bracket that are being multiplied. So this is a product, right? Now we learned a few years back that there's a rule for exponents that says when we have a product raised to the power of an exponent, we can attach the exponent to each part of that product, right, to each term. And so we can write AB all squared, let's say, equally as A squared times B squared. And so applying that rule to this little part of our equation, we can write this as 1/2 squared times the remaining x minus 3 all squared. And then, of course, the +2 at the end. And now, if that doesn't look all that different to you now, if we go a few steps further and write this as -4 times 1/2 squared is simply 1/4. we still have the rest in a form we're used to seeing. But now, this 4 times 1/4 can simplify right down to negative 4 times 1/4 is just 1 whole, right? So I could write -1, but I'll omit the 1 as the coefficient because that's redundant. And so all we have left is negative x minus 3 all squared plus 2. This is the exact same function, the exact same function as we see up here, but this is so cleaned up that we've actually gotten rid of the stretches altogether. All we have left is the negative up front, which symbolizes an Rx reflection, and we have a horizontal translation of 3, and finally a vertical translation of 2. But we have no more stretches to work with, just because we did a little bit of work algebraically, okay? This isn't always possible, this isn't always the case, but when we have well-defined functions that extend to infinity in both directions, like x squared, like the absolute value of x, like a linear function, any polynomial type of function, oftentimes lends itself to this kind of idea. Now, sometimes the algebra is so difficult and so easy, it's not even worth the work. It's not even worth the time, right? Sometimes it's better to just pop the transformations on a graph, the way we are kind of used to doing. But sometimes this can really make your life a lot easier, okay? So it's just something to look at. Again, not so much when domains in the range are restricted, but for nice functions like this is something to just think about, okay? And again, just kind of building that intuitive understanding of how vertical stretches and horizontal stretches kind of work together, okay? Because the horizontal stretch is going to make it twice as big, but because the y is related to x in a squared fashion, because we have a horizontal stretch of 2, and that 2 squared is 4, both of them working together kind of cancel each other out, okay? And now that we have a really easy function to plot on a graph, all we have to remember is an Rx reflection means that this parabola is going to be reflected below the x-axis, right? So the y values are going to go to their negative counterparts, and we can easily move around the vertex by 3 units to the right and 2 units up. So let's go ahead and do that. Let's start with our vertex. That's oftentimes a nice point to start off with, because that's a nice way to kind of grab it and translate it around the graph as need be. So we have a horizontal translation of 3 and vertical of 2. So the vertex is going to move to over 3 up 2, over to the point 3, 2, right? And now the nature, the shape of our parabola is going to be preserved because we have no stretches at play anymore, right? So it's going to be the same shape, but now it's negative, so it's going to be opening downwards. It's going to be a frown-looking parabola. And so with that in mind, we know that from the vertex, originally, we went over 1 up 1 over 1 up 1. And so again, because the shape of the parabola is preserved under this transformation, we can go ahead and go over 1, but now we're opening downwards. And so over 1, down 1, that would take us to the point 4, 1. And likewise, because parabolas are always symmetric about their vertex, about their line, about their axis of symmetry, likewise, we can go the other direction, over 1, down 1, and that takes us to 2, 1. Okay? Now to graph a few more points, just to get the shape down, we can go like we did with the original, over 2, up 4, right? Because 2 squared is 4. We can go from the vertex over 2, down 4. That'll take us to 5, and down to -2, right? And we can make a similar argument of symmetry. On the other side of the vertex, we can go over 2 to the left and down 4 to bring us to 1 and -2. And then finally, we have these points up here at +3, -3, 9. And so that means over 3, up 9, with our initial vertex in place, opening downwards, over 3, down 9, brings us to +6 and -7. So that'll be around here, -7, somewhere around there, 6 and -7. And by, once again, an argument of symmetry, the vertex means 3 over, so over 3 and down at -7 for the point at 0, -7. means we now have 7 points. That's more than enough to draw a curve through them and get the shape of our parabola going. And it extends infinitely in both directions. And now we see that the shape of the parabola is generally preserved despite my somewhat horrific graphing of the points down here below. The shape is supposed to be preserved. We have no stretches at play. All we have is a negative coefficient from the x squared term, and so that means reflection in the x-axis, but we move it around over 3, up 2, and so we don't disturb the origin. We have some translations before we open up downwards. So I hope this illustrates some of the concepts, some of the connections between the stretches and the shapes of different kinds of functions. Again, don't let this become too rigid of an idea, because it really, really does depend on the nature of the functions that we're working with, how well they're defined, and what the domains and ranges of our functions are, as to whether we can kind of do this kind of algebraic manipulation to make the transformations a bit easier to work with. But again, we could have graphed it from this form. We would have just seen the stretches meshing together a bit more in real time as we were graphing them. But again, this definitely made our lives a bit easier for this very specific example. Okay, so just keep this in mind moving forward. I hope this helps. I hope you enjoyed watching this, and thanks for watching.